Welcome to my presentation. Today, you will learn about science and practice of trend following strategies. In particular, I will describe 3 different approaches to construct a trend following systems. I will also, and importantly, on a scientific part, I will show how to represent expected returns of a trend following system into white noise, autoregressive, and fractional features of stochastic processes that drive dynamics of financial returns. I will show you some empirical analysis of outputs from these formulas, and also discuss diversification for long-only portfolios. This presentation is based on our joint work with Vladimir Lukic, and it will be available at SSRN website if you follow this link after a couple of days. It's I would like to finish certain things, and that you have the whole picture of both theoretical and practical results. So please do check this link in by next week. Well, what are trend following strategies? These are systematic strategies that trade mostly in futures markets. Generally, trend following system derive signals primarily from price dynamics. There's no alternative data, no macro, no fundamental, only purely price. There's of course some extensions of this. Nevertheless, it's purely price driven. Then, based on this classification that I will propose you now, you will not see it anywhere. Its original classification is based on my experience designing this stuff, also talking to different managers, and here we go. So what I call trend following systems are usually developed and probably executed by mostly and published also. There's a lot of interesting literature on this type of systems that I call European, and I show you later. The main difference is these are based on continuous. Like there is typically this continuous signals, continuous position sizing. You will see in a little bit what I mean. American trend following systems, they actually introduce, originate. So these are the first, like fathers of all CTAs. So in 1993, there was a idea that you could take anyone who is capable of following and following trading rules, right? And there was this class of turtle traders that they were effectively random people who were given some instructions and who had to follow the systems. And what they followed at those times, it is known today as CTAs, commodity trading advisors, or trend following systems. Some of them ended up running their own funds, and ultimately this whole industry, CTA industry, originates from this. It's typically characterized by discontinuous signals, and again I will show you in a little bit. And the last one is time series momentum. This typically you see it in academic studies. I don't know the exact reasons, but it's different from the 3. Nevertheless, I showed that empirically there is certain combination of parameters that all 3 become very correlated, even though the underlying drivers in signals of signals in these systems are very different. So what is our contribution? So there are few like European fallen systems. Why they're easy to study also? There are a few papers. They represent like a almost complete PhD type mathematical system where you can assign distributions and you can work out certain formulas. And there were few papers in this direction that were trying to analyze what are distribution properties of trend following system. We go further. We derive exact formula for expected returns of European trend following system under generic processes. And also we discuss consistency of these three systems that I described. So let me start with European trend following system. We consider, so usually we work with continuous prices of futures contract, and typically people work either with price differences or with relative returns. In particular, there are a few papers, important papers that they define, that they consider daily risk-adjusted returns or price differences normalized by volatility, and we take the filter. So usually they're filtered using the classic exponentially weighted moving average, which can be represented as a infinite recursion with infinite order. So, and the system, the weight is given by equation 2, which tells you, okay, we have a series of volatility normalized returns, we smooth it out, and we normalize by volatility. That's it. It's very simple. And nevertheless, it works. So let's go further. So and here is continuous. The important thing is that signal is continuous. Of course, there are multiple enhancements that people do. So of course, signal, you can recognize that it will be close to random variable with a unit distribution, with unit standard deviation. Of course, then you can map, say, how signal should be mapped to position. You can introduce some further adjustments, how to make discretize the continuous states, and so on. But this is basic one, and it shows that the signal is continuous. So in American trend following system, so there are few books. Usually, it's also you will see a lot. Say, if you go to these kind of books which are very high level, they never tell you exactly what they do. But nevertheless, it's based on this breakout. Usually people call them breakout rule. That's so in equation 4, I show you. So in the end, it's either use like simple moving average, or of course, I prefer to use EVMA filter, but we take prices, we compute a fast filter and slow filter. And we go initiate the position if the fast filter exceeds slow filter plus some buffer. These positions are usually their size. So once you say you signal there's a breakout, you size using this average through range, which is some sort of a volatility measure, and you also set up a stop loss, and then so the position will be liquidated when spot drops below stop loss. Otherwise, if trend continues, the stop loss will be updated. So here I can show you quickly a very quick example of American trend following system applied for Nasdaq index future. So you can see here I have, so in the end we have a band, like say fast EVMA is the green line, and it's sandwiched between like a slow EVMA plus some buffer, and when the green line, when fast EVMA is above this buffer, we create a position. So we either long or neutral or short. That's it. Very simple. Like we go short when the fast UMA is below slow UMA plus filter. So it's relatively simple, and nevertheless it works in overall, right? So here I show you how it looks like, how we generate signal, position size, cumulative PNL of this feature. Now we have time series momentum. Usually it's represented as some sort of, say, we take a rolling 12 months momentum and we take the sign, not the exact magnitude, but sign. And again, and this is like average, say, average magnitude of the direction. Right? These are kind of in between European and American system. And of course, we generalize. In paper, we show how to generalize it. And here I also show you the empirical results of applying this strategy on actual future. So as I said, this is based on, say, momentum, like say 12 months momentum, but computed at certain periods, like monthly or weekly. So in this particular example is bi-weekly. So you have these step functions as a average, like it's either positive if the price was going up, or in 2022 it was actually negative. So it went, say, average signed 12 months momentum become negative, and you have position size also going from like a random variable. So, and now I start with European trend following system. Again, most of the stuff, it works on EVMA filter, and the reason that EVMA filter allows to overweight most recent data, right? It's a very simple, of course, many other possibilities how you can increase the weight of most recent data. And so here, usually people talk of look back span. So filter is defined as a smoothing parameter nu, which is between, should be 0 and 1. And when I say, okay, I have a filter with a look back of 50 days, with a span or look back span 50 days, what it means, I use equation 9 to transfer it to kind of continuous to this smoothing parameter. Right? And it means that the data from last 50 days, it has its weight into signal, it's 50%, half. We also, what is important and why say is how it's connected to moving average. We can show that the variance of say, so we say assume that these are independent variables with certain variance. Then if we compute the variance of this filter, we actually get it that the variance of variable declines inversely proportional to the span. It's the same as you have moving average, right? But moving average, of course, it only takes data inside the span. Here we have a bit wider range, and we weight it accordingly. Usually, also what is important, since we need to properly normalize, and we do say backtests of different spans, we want ensure that all of them have unit standard deviation. And this is important, that now we are talking of, say, properly normalizing our systems, that under different parameters, the system's outputs signals can be interpreted as scores. Also, people often do this long short EVMA filter that preserves also the variance. And I show you example of here. So the first blue line, what you can see, we just use say long span, 50 days. It means that data, and we just use very simple signal that is a unit. So at current, say, imagine there was impulse unity at current time, and we see how it propagates in time. So for long span of 50 days, around 50 days, it will be right. So the integrated weight will be around 50%, right? After 100 days, effectively, impulse has gone. It's lost. Then, of course, if we use long span, right, 250 days, it's some sort of, it's a longer memory, right? We remember it longer, the signal at those spans. And usually also long short filter where, say, we are not caring about much of, say, we are not assigning short-term weight to this impulse. Is we are more interested in kind of medium to longer-term impact on the thread. Now I start looking to introduce our framework. So we work with daily returns and volatilities of daily returns. We introduce volatility normalized returns, right? And D, and then we compute our signal either as EVMA filter or long short EVMA filter, right? And our position size is simply signal times volatility target. This is just to normalize the risk of our position. Volatility target is just inverse, it's proportional to inverse volatility. And here I wanted to show you European filter, right? How does it work? So we have volatility normalized returns, the first panel, and on the right you see the distribution. So that's the purpose of this normalization of normalizing returns by volatility, that for different volatility spans between 15 days very fast when we measure very fast volatility, or up to say 1 year when we use filter span is almost 1 year. Then the distribution of these variables that enter our signal is more or less unit variance. Then we apply EVMA filter, which is variance adjusted. So effectively, it preserves the variance of data, right? So therefore, of course, it's a bit smooth. So it becomes especially long span, right? And this can be interpreted as a weight already, right? So of course, it's because you see the PDF is unit variance, almost unit variance, right? Of course, imagine we are dealing with very highly non-stationary data since Nasdaq futures since 1997, right? Once we normalize by volatility, things become more or less, or can be represented by distribution with stationary variance. I avoid, we never assume something like specific that this is normal distribution. We are not making this assumption, right? We just want things to be have stationary variance that is around the unit, so we can interpret signals as this course. Then volatility weights. Of course, it depends. When things are volatile, then we increase the position. If less volatile, we decrease the position, right? These are our weights, the D, panel D. And we also see that the weights, the distribution of weights, its unit has unit standard deviation, right? In paper, we provide all this. These are very important that exactly this is like a little bit of a magic, right? We do all these normalizations, and then we arrive to something that has almost the same unit variance. And we actually, when we took, say, realized volatility, say, cumulative P&L, now we are looking at cumulative P&L or daily P&L. And daily P&L turns out that is around 15%. We are targeting 15% volatility on this strategy, and we come up with, say, 17%, right? But this is, it means that we, first of all, we have some sort of signal indication of trend, and we also have risk control. But the most important thing now, we want to study theoretical, right? Theoretical attributions or distribution of these returns. And what we do, we consider return after, say, so we know how to compute daily returns because we have the weight. and daily return is previous weight at previous day times daily return, right? Now we have this cumulative. We want to study cumulative. And this, what I represent here in this equation is our key result. That if you recognize here, this summation, it's autocorrelation, right? It's how different returns correlate with each other at log m, and the weight of each autocorrelation term is proportional to the filter smoothing parameter in power m. So this is term related to autocorrelation, and the second term, surprise, is related to simple sample mean of the return distribution. So there are two features. One is autocorrelation, and the second is drift, like average drift. And this is this formula is a sample-based formula. So we observe realization on Z, and we can use this formula to compute. So it's really not doing like say 16, but with like using this autocorrelation decomposition to compute actual returns. Now, what is the advantage? So now we have the formula, right? This is expected, let's say, it's realized return now. Now we can, once we assign distribution to our random variables, like return, right? That drives the returns on underlying future, we can actually derive the exact formula for expected return under trend following, for European trend following strategy. This is given in equation 18. So, and surprise, so as a very interesting consequence, it's related to autocorrelation, right? And then I will explain, show you some empirical data that if autocorrelation positive, we have positive return, right? Or alternatively, the drift must be present. Now I also wanted before say I show you some empirical, it's also important to study the turnover, because trend following systems, they're high, even medium term or long term, they still is a high turnover strategies. And usually when we just do like say, usually we have different futures with different volatilities, and it's always if I tell you, okay, we have 2000% turnover, it can look scary. But actually, most of it, maybe 90% or 80%, may come from low volatility contracts like short rate futures, right? And therefore, what we do also, we introduce this 19 in Formula 19, volatility adjusted turnover. That is effectively change, turnover is change in weight, the absolute value of change in weight. We just multiply it by the volatility. So the weight for contracts with high turnover, like short rate futures, we neutralize it, we adjust it. What we also in Formula 19, it's interesting result. And actually what we show that independent of the distribution of underlying returns, your turnover will be proportional to the smoothing parameters, to the square root of span. It sounds a little bit surprising, right? But I show you examples with Monte Carlo, and this is true. So now we do, so I showed you formulas, and now we want to investigate how accurate is these formulas. If we use these formulas for, say, actual analysis of realized, say, returns, then how good we are. I have 5 minutes left. It's a lot of material, and it's important that you follow. So we start with a simple white noise process. It's very simple. It has just drift and some volatility, right? And autocorrelations here in this process is zero. And we can show that effectively the expected, say, we take 1 year, what 1 year return, and we can show the expected return is just annualized drift. Right. So no matter what the sign of the process, we generate the expected return, right? And here I show this. I show you with Monte Carlo simulation comparison. So in panel A, I show autocorrelation. There is no autocorrelation. So all driver of return is drift. So when drift is zero, so these dots are analytical formulas and bars are Monte Carlo estimates. And these are turnover estimates. So we see our formula works very well, right? It reproduces the results that we get from Monte Carlo. And in particular, it's also clear if the drift is constant, you should not trade it, right? You either constantly long or short. It's clear. Now we have a little bit more interesting process with autoregressive, short-term autoregressive process, R1, with power autocorrelation. And we can show in Formula 24 that we actually get X return. Now we have positive return when phi is positive, right? When market at diversion means that that market continues, the trend is continuous. And in opposite, if mean reversion, if auto R1 coefficient is negative, means market are mean reverting short term, it means trend following is not profitable. So here I show autocorrelation of lag returns, right? For positive autocorrelation, we have positive lags. And here how it works. So obviously, if autocorrelation is positive, and as you saw from formula, even without drift, we generate positive performance. Expected return and realized return is positive. The same with turnover. As I said, it does not depend on particular stochastic process. So now, okay, we go different examples. The most interesting one, of course, markets are complicated, and R1 process probably not a good one to describe the returns. That's long-term memory, right? A lot of research into this Gaussian, say, fractional noise. And what it shows that there's, we can also introduce in our framework, right? Because we know the autocorrelation and is what we need to derive the expected return on trend following system. And well, so here we are. So we have, and there are also like interestingly, there is a long memory, right, in panel B. So you see, in R1 process, all memory dies out after 2 or 3 steps, right? But in opposite for arithma, for fractional processes, even after many lags, like 50 lags, there is still presence, right? So in the end, there's high autocorrelation between returns at at distant lags. And of course, can be also negative mean reversion. Like in a sense, it's a mean reversion. If memory is negative, if this fractional is negative, then we have like negative autocorrelation. And this is how trend following works. It's again with even with zero correlation, but now what I have is different phis. So this is important because most likely, and what people think that in short term markets are mean reverting, but they are trading in the long term. And we can reproduce this behavior using Arfima process where phi is auto R1 term, right? That introduces negative autocorrelation, say for daily returns, but over longer periods, autocorrelation becomes positive, right? And you can see that this, even if say short-term autocorrelation is negative, right, that markets are mean reverting in short term, but if in long term they kind of follow the trend, we get positive performance at a higher, say, signal span for European trend following system is how frequently, say, we should rebalance the system. And of course, the best combination is when markets are mean reverting trend following in short and in long term. But also the green line, if we don't have anything in the short term, nothing happens, no autocorrelation, but the long-term autocorrelation is present, is still potentially is still profitable. And of course, you have different combinations when say market are mean reverting long term, but there is a positive drift. So it's a different combinations, and just to understand the impact, like say the impact of different assumptions on drivers of returns, right? What drives returns, and how we should optimize our trend following system. So of course, if we have, for example, if this last one, when markets are mean reverting in short term, but and say in short term and in long term mean reverting, but there is a positive drift. Of course, it can still make money, be profitable following the trend, but our signal span must be long term. That effectively our all P&L contribution comes that the fact that we are capturing the drift. Of course, if markets are say show both short term and long term trend following, there is a little bit of compromise, right? That if we for transaction costs, of course, this is favorable situation that no matter what span you use, you're always profitable. It doesn't happen in practice. So maybe something like a green line where we don't have short term, like maybe not strong effect. Long term, we are mean reverting. There's evidence on it, but there's a drift. We can still adjust our signal span and to have expected positive return. And this is very important. So now, finally, I wanted, it's again, we like a science, right? I want to present you a science and that everything is justified as much as possible. And there's also very interesting connection with Kelly criteria. This is actually taken from continuous time finance, that we can still justify our approach, right? How does it work? So in a classic Merton framework, we have risky asset, right? Say one asset, and a bank account, a risk-free bank account. And if we consider a value of portfolio X that invest constant weight to risky asset, and the left to the bank account, right? We obtain that the portfolio weight is portfolio value at a certain time horizon is given by this ODE, stochastic differential equation. And now Merton studied, or in few papers, he studied this problem of maximization of long-term growth. That we want to maximize, so we take, say, log, we say this will be how our log portfolio grows in time, right? We want to maximize. We want to solve problem 626. And solution is given by in formula 27. This is known as Merton fraction, or more commonly as Kelly ratio for continuous type processes. And you can recognize something that, so it's effectively it's a drift adjusted by variance. And how we write it, so this is continuous time, not related to trend following, but why it is important. And this is how you should, like in the end, it's a Kelly is how you should invest into risky asset under conditions that everything is constant, the world is constant. Look, here is have, effectively we can think of, okay, our weight is Sharpe ratio normalized by the volatility. Of course, unfortunately, in financial, or fortunately for someone, in financial markets, returns are cyclical and time varied. So we don't know exactly what is long-term the drift, or they may not exist, right? So instead we use estimates, right? So in equation 29 is equation 28, that's where we use estimates, right? We introduce some model, some statistical filter, you name it. But actually, if you remember, in European trend following, it's very, very much resembles European trend following system. Because when we apply EVMA on the risk-adjusted returns, is nothing more than estimation of EVMI filter of daily sharp ratios. And in the same way, we adjust it by volatility, right? So that is, it looks like miracle, right? That we enable, we take something out of shelf, but we can connect it with continuous time series. We can connect it with expected returns under certain stochastic processes, and this is your science, right? And I just quickly, just to make sure I have time, according to my estimations, I have a few minutes to go. I leave it, the next empirical part, I leave it for you to read the paper, but we also show you actual, like using actual futures, right? Actual futures is relatively liquid universe of futures with some actual transaction cost. And of course, what we do, right, is we find a certain, what I like about trend following systems that we have, we just have two parameters for European. It's a long filter and short filter. And we can find the optimal combination of these parameters that optimize not only Sharpe ratio, but also defensive profile of Sharpe ratio and somehow reasonable transaction costs, right? For American systems, the same. For time series momentum, the same. And I choose some optimal parameters and I compare it with SG trend index, which is industry standard benchmark. And I can show you that these kind of lines, right, they are very highly correlated. This is one of the reasons I wanted actually to show you different ways to construct trend following systems, but in the end, they're highly correlated. And for me, it shows that uniform laws, right? There is uniform formulas, like say science, for European type of trend following, we can do some equations, but there are more, for me, more ad hoc approaches, but in the end, it all works. So, and I leave it, the rest, I leave it for you to read the paper. And here, I think I see that we have 8 questions. So one question is interesting. So do you find the derived relationship between autocorrelation structure and trend following P&L holds consistently across asset classes, say commodities, rates, and equity indices, or there are more specific deviations? That's a good question. Yes, we provide historical analysis, and what doesn't work is FX. FX tends to have more mean reversion. Otherwise, yes, we have direct as a relationship that is consistent across asset classes. Okay, and this concludes my talk because we run over time. So please have a look at our paper and have a nice day. Enjoy it's a terrific pipeline of speakers. Enjoy the rest of your day. Thank you.